Okay, so now what we need to do in this lesson is to talk about something called a rate law. And then we're going to use a technique called initial rates to determine this thing known as the rate law. Okay, so rate law. What do I mean by a rate law? Well, it's an equation. And what it does is it relates the rate of a reaction to the concentration of the reactants. So if we have a generic chemical reaction like this, A plus B reactant give us product P.
I pity the fool goes home crying to his mama.
The general form of the rate law would be the rate of the reaction is equal to K, which stands for something we'll explain in a second, times the concentration of reactant A raised to some power we're calling X, times the concentration of the other reactant B raised to some power Y. Okay? So the K, that is the rate constant. And a couple things about the rate constant. First of all, it changes with temperature. So if you change the temperature, you get a different rate constant. And the other thing about the rate constant is that, and the name kind of gives it away, it's a constant that gives you an idea about how fast the reaction is going. And of course, the brackets indicate concentrations. So these are the concentrations in molarity of the different reactants. And the exponents, X and Y, those are what we call the proportionality exponents. They represent the proportionality between each reactant concentration and the rate of the reaction. Okay, so a lot of what you're going to be doing is figuring out what those exponents are. All right, so the first thing you have to do is you have to pick a reactant to hold constant. So let's just say that going from the general form of the rate law that we just looked at, we're going to hold the concentration of B constant. Now on your handout, that's not crossed out, but just to make that clear, if you want, you just cross it out on your own. So we're going to hold the concentration of B constant. So the idea there is that any change in the rate, does it get faster, does it get slower, does it stay the same? Any change in the rate is due to the change in the concentration of A. So then we're going to change the concentration of A, and we're going to see what happens to the rate. Like I said, does the rate get faster? And if it does get faster, did it double? Did it quadruple? What happens? Okay, so again, let's think about different possibilities. So we're going to change the concentration of A. Well, let's say that we double the concentration of A. And so then the question becomes, well, what exponent would X need to be if I double A and it causes the rate to also double? So if I double A and the rate doubles, what exponent would X be? So it would look something like this. So what we have in blue is the original rate law. And the red 2 represents the changes that we see. So I change A by a factor of 2. I double the concentration of A. And if that causes the rate to double, since everything else is the same, all the blue stuff is just something we could factor out because it's the same, we can kind of pull out of this equation all of the red characters. And so that allows us to figure out what the value of the exponent is, what X is. So if 2 needs to stay 2, then the value of the exponent X should be 1 because 2 raised to the first power is 2. So that means that X is equal to 1. Well, what if the rate quadrupled? So again, we doubled A, but now the rate went up by a factor of 4, it quadrupled. So once again, we just pull out the stuff that changed, all right? And we use that to figure out what the exponent is, what X is. And so in order for me to convert that factor of 2, that multiplier 2, into a multiplier of 4, what exponent do I need to put on it? Well, 2 squared is 4. So in that case, that exponent X is equal to 2. Okay, well, what if the rate went up by a factor of 8? Okay, so that would look like this. So again, if the rate was multiplied by 8 when the concentration of A was multiplied by 2, well, what exponent do I need to put on that 2 in order to convert it into an 8? Well, X in that case would be 3 because 2 cubed is 8. 2 times 2 times 2 is 8. So that means that the exponent would be 3. And so then you just do something similar with B. You would hold A constant and you do similar experiments with B to find the other exponent, to find Y. Okay? Now, that seems pretty abstract, I know. So you may be a little intimidated by that, but there is a more formulaic way to do this that I'm going to show you now. So what you want to do is you want to set up a proportionality. And so again, we'll use the general form of the rate law, that we've been working with, and we're going to hold B constant. So it would look like this. Compare the rate in experiment 2 over the rate in experiment 1, set that equal to the concentration of A in experiment 2 over the concentration of A in experiment 1, and raise that to the power of what you're solving for, that exponent x. All right, so now let's just do an example. So we're going to apply this equation to this setup. So the rate in experiment 2, as you can see, is 0.25 units of molarity per second. So the rate in experiment 1 is 2.0 molarity per second. And so that's equal to the concentration of A in experiment 2, so that would be 0.5 molar, over the concentration of A in experiment 1, so 1.0 molar. And all of that are raised to this power of x, okay? So if you were to plug this into your calculator or whatever, you would see that it comes out to 1 over 8, right? Because there's 8 25s and 200. Now 0.25 divided by 2 is the same thing as 1/8, right? Or 0.125. And so that's equal to, and this of course is 1/2, right? 0.5 over 1. So then you can kind of just think about it logically. What exponent would I put on 1/2 to make it equal to 1/8? Well, 1/2 times 1/2 times 1/2 equals 1/8, right? So that's means that x is equal to 3. It's cubed. So x is equal to 3. So using the numbers from the experimental data, we can apply this equation, plug them in, make the substitutions, and just solve for that exponent as well. Okay, so same thing, 0.25 over 2.0. Take the two rates. 0.5 over 1. Take the two concentrations. Raise to the power of x. So you rearrange, you just simplify. 0.125 equals 0.5 raised to the power of x. Now the other way to do this is you could just take the log of both sides and use that to solve for x. Okay, you take the log base 10 or the natural log of both sides. Okay, so the log of 0.125 equals x times the log of 0.5, because remember that whenever you take the log of something with an exponent, that exponent comes out as a multiplier. All right, so then you just plug that in your calculator. The natural log of 0.125 is negative 0.208. X times the natural log of 0.5, which is negative 0.693. So then you can just divide both sides by negative 0.693, and you see that x then, once it's isolated, is equal to 3. Okay, so why did we do that? Why do we try and figure out those exponents? Because those exponents tell us what's called the order of the reaction. Now, the order of the reaction is just a classification that describes how the rate of the reaction depends on the concentration of the reactants.
What?
So there's different orders you can have. There's zero order, and that's when the rate depends only on the rate constant, depends only on K. Now, the other way of thinking about that is that it doesn't matter what the concentration is, you're going to get the same rate. And that's because the exponent on your concentration is equal to 0, right? Because anything, let's say that it is concentration of A, when we say it's zero order, that means it has an exponent equal to 0. And so anytime anything raised to the power of 0 equals 1 by definition. And so if there's a rate constant out there, that's just like the rate constant times 1.
What?
Okay, the exponent equals 0.
Huh?
And then the other, or in other situations, if you have a first order relationship. In that case, the rate is directly proportional to the reactant concentration. So for example, if the reactant concentration doubles, then the rate of the reaction also doubles.
Huh?
And in this case, as you can probably guess, the exponent is 1. Now remember that in chemistry, most of the time we don't write ones. Ones are implied. We don't write ones as subscripts or as coefficients or as exponents. They are implied. Okay. Another reaction order could be second order. And so that's when the rate of the reaction is proportional to the square of the reactant concentration. So in other words, if we double the reactant concentration, it quadruples the rate. Okay, that's what second order means. And of course, you're probably guessing that the exponent in the case of second order is 2. So since each reactant has an order, you can say that the overall reaction has an order as well. Okay, so each reactant has an order and the reaction has an overall order. All right, so how do you figure that out? Well, you just add the orders up. So in the case of our generic rate law, we just add the exponents together. So the sum of x plus y. So once again, let's say that this is a reaction that we have. We have reactant A reacting with reactant B, and the reaction stoichiometry is such that the two A's react with one B to produce the product C. And let's say that we figured out by experimentation that the rate law is the rate constant K times the concentration of A squared. Okay, so now let's figure out, well, what is the reaction order for A? What is it for B? And what is it overall? Now, it's based on the rate law. It's not based so much on what's going on in the reaction. You answer this question from the rate law. So A has an exponent of 2. So we can say that this reaction is second order in A, or second order with respect to A. Now notice that the rate law has nothing about B in it. So another way of thinking about that is, it's like this is multiplied by 1, which, remember, that came from the fact that the concentration of B must have an exponent of 0, okay? So that means that it is 0 order with respect to B. And so since the overall reaction order is just the sum of the two, then that means that the overall reaction order is also 2 plus 0, which equals 2. Okay, so now we want to utilize this information to do a problem like this, which is a common kind of problem from this unit. You definitely want to know how to do these, so I'll do some examples and give you opportunities to practice. So we're going to look at this experimental data. In this table, you see 3 different experiments. And we're going to use the data from these experiments to figure out what the rate law is. So first of all, we need to find 2 experiments where one of the reactant concentrations is held constant while the other one changes, and we observe how that affects the rate. So notice how that we compare experiment 1 versus experiment 2. I hold the concentration of B constant, okay? So the concentration of B stays the same, they're equal. But what happened with concentration of A is that I doubled it. I multiplied it by 2. Okay. Well, what happened to the rate of the reaction when I doubled the concentration of A? Well, it also went up by a factor of 2. Okay. So again, this is directly proportional. So if I doubled A, I double the rate. So that means that A must be first order. Okay, because doubling the concentration of A doubles the rate. Okay, so now I need to find out what the order for B is. And in order to do that, I need to find 2 experiments where A is held constant, but B changes. And so I'll do that by comparing experiment 1 versus experiment 3. Because if you look, A stays the same between experiment 1 and experiment 3, but the concentration of B changes. It goes up by a factor of 3, so it's multiplied by 3. Okay. Well, multiplying the concentration of B by a factor of 3 causes the rate of the reaction to go up by a factor of 9. Okay? So what exponent would I put on this multiplier to get this multiplier? What exponent would I put on 3 to get 9? And of course, we know that 3 squared equals 9. And that's the squared part that's most important. So this one is second order in B. Okay, and remember that the overall reaction order is just the same, or pardon me, the sum of the 2. And so the overall reaction order is 3, okay, or third order. So once you know the reaction order, then you can write the rate law. Remember that the rate is equal to the rate constant times the concentration of each reactant raised to the power of its reaction order. Okay, so since we said that A was first order, its exponent is 1. We said that B was second order, so its exponent is 2. But again, in chemistry, we typically don't show 1s. So in order to find the reaction order of A, I need to find 2 experiments where B stays the same, but A changes. Well, once again, that's experiments 1 versus 3 for where B stays the same, they're equal, but A changed. Okay, so by how much did A change? Well, the simplest way to figure that out is you divide the bigger one by the smaller one. So 0.819 divided by 0.273. So if you do that math, then you get 3. Okay, so this initial concentration was increased by a factor of 3. And so now we see what happens to the rate. Well, again, we can just figure out the factor that it changed, by which it changed, if I just compare the two. So we'll divide the bigger one by the smaller one again. So 25.47 divided by 2.83, and you get 9. Okay, well, again, what exponent would I put on this multiplier of 3 to get this multiplier of 9? Well, 3 squared equals 9. So it must be second order in A. Okay, so now let's do it for, so it was second order in A. So now let's do that for B. So I need to find 2 experiments where A is held constant. That's these 2 experiments, 1 versus 2. So those 2 concentrations are the same, but the concentration of B changed, okay? And perhaps you can see that it doubled, right? 1.562 is about 2 times 0.763. So this went up by a factor of 2. Well, what happened to the initial rate? The initial rate didn't change, okay? No change. So what that means is changing the concentration of B has no effect on the rate at all. So remember what that means. That means that the exponent on the concentration of B must be a 0, because it just becomes a multiplier of 1. So that means that this is 0 order in B. And so the overall reaction order is just 2 plus 0, which is 2. Okay, and so then to write the rate law, remember that the rate is equal to rate constant, lowercase k, times the concentration of each reactant raised to the power of its reaction order. So A is second order, so I put an exponent of 2. And B, we said just now, is 0 order. And so that kind of becomes 1. And so the more conventional way to write the rate law would be, that the rate is equal to the rate constant times the concentration of A squared. Second order, 0 order, overall second order, and the rate law is just rate equals rate constant times concentration of A squared. Okay, so now what I would like to do is to go over what I'm going to call a slightly more difficult example of determining the rate law and the rate constant for a reaction when you're given this table of experimental data based on the initial concentrations of your reactants, and those initial rates have been determined. So we know that always the rate of reaction is equal to the rate constant, and then you multiply that times the concentration of each reactant raised to some power. We'll just call the exponent for the nitrogen monoxide X, and for the hydrogen Y. Okay, so in general, I know the rate law has this form. And my job really is to determine what the value of X is and what the value of Y is. So the way we do that, I'm going to do it in 2 different ways. First of all, we'll look at the sort of the simple way where you just analyze the data in the table and just think about it logically. And then for the second one, we'll have to actually do a calculation so you can see how that works. Okay, so let's compare, first of all, experiment 1 with experiment 3. Notice that the concentration of NO stays the same, but the concentration of H2 has gone up. It's been doubled, right? So this concentration stayed the same, this concentration was doubled. And so now look at the effect of that on the rate of the reaction, the initial rate of the reaction. It was 0.006, now it's 0.012. So that also went up by a factor of 2, it doubled. So if this stays the same, if I held that constant, this change in rate must be due to this change in concentration, the change in concentration of the H2. So what I can get from that is the exponent y. And that is going to be y equals 1, right? Because this doubled and the rate doubled. So they are directly proportional. So that means it's a first order with respect to hydrogen. Okay, so now I know that the exponent on hydrogen is equal to 1. And so I'm going to utilize that information in the next part. So let me erase the information there, and we'll go to
Excuse me?
Screen here. Well, this is just repeating something that I already told you or figured out.
Excellent.
That stayed the same.
You're a bunch of bloody magicians.
That doubled.
Oh, indeedly doodly.
And the rate doubled. So for me to figure out that that exponent y is equal to 1. What we know so far is that the exponent on the hydrogen is equal to 1. So we know that the exponent on the H2. So now what we're going to do is we're going to use the ratio method of experiments 1 and 2 to determine what x is. You have to figure out 1 first before you can employ this ratio method. And the reason why this is a slightly more difficult problem, and the reason why we have to use the ratio method here is because you'll notice that there are no 2 experiments where the concentration of H2 has stayed the same. It's different each time. So that's why this one is slightly more difficult, because we can't do for the nitrogen monoxide what I did for the hydrogen. You can't just look at a situation where you have 2 experiments where the hydrogen stays the same and only the nitrogen monoxide changes. We don't have 2 experiments that fit that, that need. So what we're going to do is we're going to do the ratio method. So remember how we do that. Okay, so now what we're going to do is we're going to compare the rate of experiment 1 to the rate of experiment 2. Okay, and of course that's equal to the rate constant for experiment 1 and the rate constant of experiment 2. But I know that those are going to be the same, because this is just something that is a characteristic of the reaction and the temperature of the reaction. So we're going to just kind of cancel those out. Those will just cancel out each other. And so since we're talking about the rate of experiment 1, in this case, it's going to be the concentration of NO in experiment 1 times the concentration of H2 raised to the power of 1. I don't know what the exponent is there, so I'm going to put the x there. But I know that this is an exponent of 1, and I'm going to use the concentration from experiment 1. And that's over the concentration of NO raised to the power of x in experiment 2, okay, times the concentration of H2 raised to the power of 1 again in experiment 2. Okay, so now I can just substitute in the numbers there. Okay, so first of all, I'm going to do it down here. So the rate in experiment 1 was 0.00600. Now I'm going to leave off the units just because my penmanship is bad and it just saves space, but recognize that units are usually very important. But for this particular type of calculation, sometimes it does benefit just to leave the units out, so you don't get kind of lost in all of that stuff. And then I'm going to divide that by the rate of experiment 2, which is 0.144. 0.144, okay? And so like I said, these cancel because they're going to stay the same. So I'm going to go ahead and put in the numbers here. So the concentration of NO in experiment 1 is 0.01 raised to the power of x. Concentration of H2 is 0.01. And I know that that's raised to the power of 1. And so the concentration of NO in experiment 2 is 0.02. Okay, once again raised to the power of x, and the concentration of H2 in experiment 2 was 0.03. Okay, and again, I know the exponent on that. That's an exponent of 1. So you can kind of see how this is going to play out. You just do the math at this point, and you're going to use algebra to isolate x. Okay, so I'll erase that and let PowerPoint do some of this in better penmanship. Okay, so the rate of experiment 1 divided by the rate of experiment 2 equals the concentration of NO in experiment 1 raised to the power of x times the concentration of H2 in experiment 1 over the concentration of NO in experiment 2 raised to the power of x times concentration of H2 in experiment 2.
All we want to do is pump you up.
Okay, so you plug in the numbers from the table, right? And so we're going to move on to the next screen now.
I'm going to go call the psychic hotline. They'll know what to do.
Don't call the psychic hotline. This is pretty simple. You may have to review some algebra as to how to isolate that x, but I'll also show you in this example problem. Okay, so this is kind of where we left off. So these are the numbers that we left off from the previous slide. And so, hopefully you notice something here, that a lot of these can, or I should say, simplify into more intuitive type fractions. Like this is essentially 1/2, and this is essentially 1/3. Okay, but this one also is a fraction that we can work with. If you look it up, it's, 24 times 6 is 144, so it's 1/24. Right? If you do that math, plug it into your calculator if you want to. equals 1/2 raised to the power of x. Remember, if due to, again, just the mathematical properties, if there's an x in the numerator and the denominator as an exponent, then we can kind of combine those as an exponent with a whole fraction, right? If you're doing the same thing to the numerator and the denominator, then you can bring it out and just do it to the whole fraction. So 1/2 raised to the power of x times 1/3. Okay, so now I can just rearrange and solve for x. So I'm going to multiply both sides by 3. That's one thing I'm going to do. Okay, so I'm just going to, multiply this by 3, multiply that by 3. And so that way I get rid of the 1/3. And so that becomes 3/24, right? 3/24 equals, which remember that's 1/8. Okay, because 24 is 3 times 8. So that's essentially saying 1/8 equals 1/2 raised to the power of x. All right, so just look at it in PowerPoint. So that changes into 1/8 equals 1/2 raised to the power of x. I can just take the log of both sides if you want to, and you figure out that x is equal to 3. So now you have the rate law. The rate is equal to the rate constant times the concentration of NO raised to the power of 3 times the concentration of H2 raised to the power of 1. Okay, but we haven't answered the question yet. The question said, what is the rate constant? What is K? So now let's talk about how to get that.
Hey, this is great, man.
So what we're going to do is all of those experiments, experiment 1, experiment 2, experiment 3, they all have to obey this rate law. So I can just use the numbers for any experiment and plug them into this rate law and then just rearrange and solve for the rate constant K. So that's what we're going to do. Okay, so I need the data. There it is. So the rate is 0.012. Okay, K, the rate, pardon me, the concentration of NO is 0.01, but we got to cube it, times the concentration of H2, which is 0.02. So you just rearrange and solve for the rate constant. And here's where the units actually are important, because the rate constants have different units based on the order of the reaction. In this case, the order of the reaction overall is 4, right? Because you add the two exponents together. So the exponent of 3 plus 1. So the overall reaction order is 4, which is very rare, but this is just an example. And so the rate constant will have units corresponding to the overall order of the reaction.
Yes, indeed.
Okay, so we're going to rearrange and solve for the rate constant. And if you do that math, it comes out to be 6.00 times 10 to the 5th inverse molar cubed inverse minutes. Okay? All right, so hopefully that helps you understand this method of initial rates a little bit better. And definitely you want to practice these as much as time allows, because this is an important topic from this unit. That orders of reaction don't have to be whole numbers, but in general chemistry, we take things one step at a time. That's really what we're going to focus on. Those reaction orders being nice, round, whole numbers. And as I said, typically the reaction order is 0, 1, or 2. Zero order, first order, or second order. But it is possible to have third order and higher, but that is very rare. Okay, so now what I want to do is I want to use this data table, and we're going to use the more formulaic way to solve for the rate law to answer this question. What we want is the rate law, and then we want to use the rate law to calculate the value of the rate constant. Okay, so remember the equation that I said could be used anytime you hold one of the concentrations constant and you change the other. So in this case, if I compare experiments 1 versus 2, right, these two concentrations stay the same, where this one changes. Okay, so it's pretty obvious that this went up by a factor of 2, but let me just go ahead and show you how to calculate it with that equation that I demonstrated earlier. So remember that the general form of the equation is you take the rate in the one experiment, so we'll say experiment 2, and you compare it to, or divide it by the rate in the other experiment. So in this case, we'll say experiment 1. And so that's equal to the concentration of, in this case, NO2 from experiment 2 divided by the concentration of NO2 and experiment 1. And all of that gets elevated or gets raised to the power of some exponent. We're going to solve for x. We're going to solve for that exponent. Okay, so we're just going to substitute in the numbers from this data table. So the rate in experiment 2 is right here, 6.8 times 10 to the minus 8. Okay, so the units on this, as you can see, it says moles per liter, but remember, again, that's what's molarity, right? Per hour. So instead of per second, now we're doing per hour. Okay, and then divide that by the rate in experiment 1, which is 3.4 times 10 to the minus 8th molarity per hour. And that's equal to the concentration of NO2 in experiment 2. So that's this one right here. So 0.700 times 10 to the minus 4. And that's, again, concentration of molarity over the concentration in experiment 1. So 0.350 times 10 to the minus 4 molarity raised to the power of x. Okay, well, this simplifies. If you were to plug this into your calculator, you would see that this is basically 2, okay? And that's equal to 2, right? 0.7 divided by 0.35, and that's raised to the power of x. Well, what exponent should I put on a 2 to keep it a 2? 1. Okay, so that means that it's first order with regard to, or with respect to, NO2. So it's first order. Okay? Now you can do something similar to figure out the order of the reaction in carbon monoxide, CO. So let me erase all this and I'll do that. Okay, so once again, we start with looking for 2 experiments that have the concentration of NO2, which I know now is first order. That's held constant, right? So that's these 2 experiments. It's the same. And this one changes. It goes up, right? It goes from 5.1 to the 5.1 times 10 to the minus 4 up to 1.02 times 10 to the minus 3. Okay, so once again, let's just apply the equation that the rate, in this case, experiment 3 over the rate in experiment 1 is equal to the concentration of CO in experiment 3 over the concentration of CO in experiment 1 raised to some power x. You could say x. You could call it exponent y if you want to, just to make them distinct. But the idea here is that that's the unknown that we're going to solve for. So we can just substitute in the numbers now. So the rate in experiment 3, once again, is 6.8 times 10 to the minus 8. And I'm leaving out the numbers, or pardon me, I'm leaving out the units just to make it a little bit cleaner. But it's always my recommendation that you write out the units so that you can see how things cancel. And that just helps you figure out if you make a mistake, where you have made a mistake. Potentially. So the rate in experiment 1 is 3.4 times 10 to the minus 8, okay? And that's equal to the concentration of CO in experiment 3. So that's 1.02 times 10 to the minus 3. And the concentration of CO in experiment 1 is 5.10 times 10 to the minus 4. And then again, that's raised to the power of x. Well, if you plug this into your calculator, once again, you'll see that this is equal to 2. And this is also equal to 2 raised to the power of x. And so same thing as last time. The exponent needs to be a 1 to keep 2 as a 2. So that means that it's also first order with respect to the carbon monoxide. So now that I know what the order of the reaction is for each of the reactants, I can write a rate law, and I can use the rate law to figure out what the rate constant is. Okay, so the rate law is just equal to the rate constant times the concentration of each reactant. So the concentration of CO, I know that it's first order, so I'm going to not show it. It's implied that there's an exponent of 1 there, times the concentration of the other reactant, NO2. And once again, that has an exponent of 1. It's implied. I'm not going to write it. So this is the rate law right there. That answers the first part of the question. Determine the rate law. Okay, so now for the second part of the question, calculate the value of the rate constant. The idea here is that every one of these experiments follows this rate law. So what I can do is I can just pick one, and I can substitute in the numbers from the data table and rearrange and solve for the rate constant. So since it's the closest one, let's just go ahead and use experiment 3. And so the rate experienced in experiment 3 is 6.8 times 10 to the minus 8th molar per hour, sorry. And that's equal to the rate constant times the concentration of carbon monoxide, which is 1.02 times 10 to the minus 3, and that's in units of molarity. And the concentration of NO2 is 0.35 0 times 10 to the minus 4. Once again, units of molarity. So then you just rearrange and you solve for the rate constant. Okay, so basically that means I'm going to figure out what this product is and then divide both sides by that number. And then I'm going to let PowerPoint actually do the calculation, but you're just going to rearrange and solve for the rate constant. Okay, and notice that when you do, what you end up with are units for this rate constant of molarity to the minus 1 times hours to the minus 1, or inverse molarity, inverse hours. So there's your rate law, because it's first order in CO, it's first order in NO2. And so as I said, you substitute in the data from any experiment. In this case, I didn't use experiment 3, I used experiment 1. Plugged in the numbers, there's the rate from experiment 1. There's the concentration of carbon monoxide in experiment 1. There's the concentration of nitrogen dioxide in experiment 1. And you just solve for the rate constant K. And you get, in this case, 1.9. Liters over mole hours, that's the same thing as like inverse molarity, inverse hours. Because remember the molarity, since it breaks apart into moles per liter. And if you flip that, if you did the reciprocal of that, it would be liters over moles. And then the hours is also in the denominator.